Okay, so this one is the last part of the lecture for today. So we have the same problem, but problem part 2. Again, we have 15 samples, the same. We have the same data, okay? So the question says that as a manager, so you did a customer survey, okay? And then you found out that the customers, they don't want any bulb with lifetime lower than 600 hours. Okay, this is the first part. The customers, they don't want anything less than 600 hours. And also, you ask the design team says that any light bulb, the headlight bulb, higher than 1100 hours is not possible with the manufacturing equipment you have. Okay, so what it means is that, so these two of them, so the result says that this is the continuation of the problem. So this is the second part of the problem. Okay. You cannot, not you cannot, that is means that your tolerance is between 600 and the 1100. Okay. So if you remember, our data points, our graphs, everything, but this is the this is not statistical. So this one is not statistical. This is set by, this is voice of customer, you can say. The customer doesn't want anything less than 600 hours, and the design team says that anything more than 1100 hours is not possible. So your tolerance is between 600 and 1100. So the lower specification limit, this one is the lower specification and then limit. Lower specification limit is 600, and then upper specification limit is 1100. So this is the, you can say this is the target, or you can say the goal. Okay. These are set by customer or designer. Okay. This is not statistical. Okay. So the question now comes, how capable is your manufacturing facility for this one? What is the capability? So the second question is that, can you do that? If you can, what is the quantity? Well, how can you quantify it? I mean, this is this first part of the question. How capable is this one? You have to look for the, again, statistical. Statistically, can your manufacturing facility do that? The second thing is that the centeredness of your manufacturing process. So centeredness means that how centered are your real values. So you are looking for how centered are your real values with respect to this. So with respect to the specification limits, okay? How centered are your values with respect to lower specification limit and the upper specification limit? These are the two questions, yes? Okay, these are the questions that we need to answer. First, how capable is your manufacturing facility? Second thing is that the centeredness of your manufacturing process. Okay, let's start. So the first thing is that this one is the same data that we had. So it means that we had 15 samples, and then each sample we had the 4 bulb. Okay, this is the histogram. So we are rotating that histogram this way. So because, I mean, generally the books use this version, okay? So the book, okay? So we have the same data, 15 samples, and then 4 bulbs, okay? And then the question is that we have to look for the process capability. But as you can notice here, this one looks like a normal probability. Normal probability, or the bell curve, or it's also called the Gaussian curve. Okay. So let's check firstly for the process capability. What does it mean that process is capable or not? Again, if you use the central limit theorem, you can use you'll get the final form, which is the normal distribution. Okay, this is the central limit theorem. Okay, so let's check it now. What is capability, and then what does it mean that process is capable or not? So from the problem, we had the upper control limit, we had the lower control limit, and we had the control limit. Now I will put all of them on this chart. You can see this is the lower control limit. These are from the Excel. Yes, we did it. So these are from Excel. So we did that. The lower control limit 538. So let me just go to Excel. You can see the lower control limit for X bar chart. It is 538. The upper control, the center line is 900. You can see the grand average, which is 900. So this one is grand average. And then low upper control limit is 1200. You can see 1262. This is the upper control limit. These are all from Excel. Okay, so we are trying to understand what it means for a process to be capable. So the capability of a process, what does it mean? So we are trying to understand it, and then we will see, can our manufacturing process do what the customer wants? Can it do it or not? If not, then we have to find a solution. Okay. Then now we will add the specification limits set by the customer and designer. This is by customer, and this is by designer. You can see this is the control limits of our process, and this is the specification limits of the customer and the designer. Let me write it this way. Yes, this is our manufacturing facility. Okay, and this one is limits set for us. Set for us. So the first limit, this one is by customer. The second limit, this one is by designer. Okay. Designer says that we cannot manufacture more than this one. And then customer says that you cannot go lower than this one. Okay. So the question is, we have to look for the process capability index. Okay. This index will tell us how capable is our process. And then this range here from statistically, this range is called, this part is 6 sigma. And then six sigma, 6 times sigma. And this sigma is the standard deviation. This one is for normal distribution. Okay. For normal distribution, the lower control limit to upper control limit is equal to 6 times sigma. This one is 6 actually. And this one is sigma. Okay. And then we have the specification limits by the customer and the, as I said, the designer. Okay. So the capability index tells us this one, the specification limits divided by the 6 sigma. Okay, but the sigma is, this one is approximate. Since we don't know, okay? Since we don't know. So we don't know the population sigma. Okay. Since we work with samples. Okay, since we work with samples, we don't know the population sigma. So we are trying to approximate it. How do we approximate it? We use either this formula or that formula. Okay, sigma is equal to S bar by C4. This one is approximately equal to also the R bar by theta. Okay, this is what we use for the 6. And then if CP value, if this value, if I go back, so what we do is that we are comparing this range. So this range, which is UCL minus LSL, we are comparing this range with that range. You can see this part from LCL to UCL. We are comparing these two ranges. Okay. And then if the range here, this one, so you are doing that UCL minus LSL, and you divide it by the 6 sigma. This one is, as I said, approximately equal to UCL minus LCL. This one is approximately. And this is the specification limit. If this specification, the specification limit divided by this 6 sigma, and that is CP. Okay, you are comparing the range here with the full range. Then if this CP value is greater than 1, okay, this is the desirable. Desirable because now it is not good because the real values that you have, this one, you can see is larger than the specified limits, which is not good. This is not good. Your manufacturing facility is not efficient, you can see, because it manufacturing headlights that the customer doesn't want, and designer cannot do that. Okay. So now let's look at it. The first case is that you can see this is not good. So this is not desirable. We want something this way. Okay, you can see the specification limits are more than what we can do. This is good actually, yes. This one is desirable. Okay. But this one is not desirable because we are not in the specification limit range. And if we are in the specification limit range, this is desirable. Okay, now let's do that calculation for our problem.